Morning, my name is Zach Franken, and we're here to talk about access control systems and a little bit of biometrics. Now, I'm going to whiz through things quite quickly at the beginning because I really want to get you up to speed to see some of the vulnerabilities. So, we're going to talk about an overview of physical credentials. These are cards and tokens, things that you can actually hold. I'm going to take you through a brief overview of some of the biometric systems around, and I'm going to take you through a worked example of how one of these biometric systems work. And then I'm going to give you a little overview of an attack that's common to most of these systems, and a demo, which may or may not work, as all demos do. So, this is a basic access control system. You have the access controller itself, a lock, an electric lock for the door, normally these days some sort of reader. This could be a biometric device also, and generally on the inside an exit device, a push to exit button, or sometimes it's even a small passive infrared sensor mounted directly over the door, so when you approach the door from the inside, it unlocks. Not always a good thing, by the way. It's great for ease of use, but if the door has any gaps underneath it, you can normally wave things underneath and trip that sensor off and just unlock the door like that. Now we have a slightly more advanced system here. This has a local door controller, and it talks to the access control system normally by, it could be by modem or RS485, and the access control system pushes a set of credentials to the door, and the door then locally verifies those credentials. And periodically the access control system will pull the door controller and pull off the logs as to who went through the door. And this could be real time also. With the anti-passback system, you tend, even though there's a regular door shown here, it tends to be a man trap or a turnstile. The whole idea is when you enter the building, you can't pass your card back to your friend behind you and have him swiped through also. It also keeps track as to who's in or out of the facility, because you have to scan to get back out. So, as far as physical technologies, we've got the Magstripe card. Everyone's got one in their pocket. A WIGAN card, you may have one of these, but they're a little bit old these days. A proximity card, again, I think most of you will probably own one. A Barium Ferrite card, a little bit of old tech as well. And the concealed barcode card. I'll get to that in a moment. And of course, smart cards, which include things like smart proximity cards, contactless smart cards. So, here is the concealed barcode card. It is as crappy as it sounds. Basically, what you have is a barcode on the bottom of the card, obscured by a little strip of plastic that's permeable to infrared. It is just fucking embarrassing, I have to say. If you know anyone that actually uses one of these cards as a credential, I strongly suggest that you point and laugh. Because anything that can be duplicated with the aid of a flashlight and a photocopier, and they can, is not up to much. So moving right along, we've got the Magstripe card. In general, 3 tracks. Your standard credit card will have 3 tracks. And there's 2 types. There's high coercivity, HICO cards, and local cards. Generally, your Visa card is likely to be a low coercivity card, and it's just the amount of energy that it takes to flip the magnetic bits. I know that, for example, a California driver's license is a high coercivity card, so quite often simple readers won't be able to rewrite the data on the card. They're read by an exposed head in the reader, which can lead to some problems. You can mess with them a little bit. And sadly enough, for example, your hotel door key that you've probably got in your pocket is considered to be a high security card. And high security in the Magstripe access card industry can mean simply offsetting the tracks, getting a little jeweler's screwdriver out and tweaking that head down a couple of millimeters so a standard card reader writer won't necessarily be able to read and write on the tracks. Shocking, really. So generally, these Magstripe readers, the classic protocol that they talk is a thing called clock and data. So here you see the clock, regular pulse that comes out, and the clock basically specifies what the data line is doing. So on a clock pulse, it's going to look at the data line and work out whether it's actually sending a 1 or a 0. So this is what clock and data looks like in the real world. This is actually my Visa card. I hasten to say it's a very, very small piece of my Visa card. But this is clock and data in real life. So we have the Barium Ferrite card. This tends to use an insertion reader, but the ones I've seen around today, you literally take the card and you place it flat against the reader. And it has a whole lot of little magnetic zones on the card, as you can see here, which are polarized and in various positions. It's pretty much a slightly fancier version of a punch card. And if you crack one of them open, you'll see the barium ferrite material, which looks very much like a fridge magnet. And it was marketed as the original card key. So card key TM were barium ferrite cards. And then one of my favorites, the Wigand card. These are still used today. For example, all the security IDs at many airports use Wigand technology. So it has embedded in the card tiny strips of a special wire, and half of the wire, is coaxial, and the wire is on the outside, I believe it's in tension, on the inside it's in compression. And they lay these little snippets of Wigand wire out in a pattern like this to create their code. So basically on the top you've got the ones, and at the bottom you've got the zeros. And as you swipe it through, you get your bits read off the card. Now, this is what a Wigand card actually looks like. If you hold it up to the light, and I have to say this was quite a bright light, you get to see the actual bits themselves, the bits of wire sitting in the card. And it's entirely possible to take a Wigand card, cut it open, and actually rearrange these little bits of Wigand wire into a new code. It's not too hard. Part of the security was in the manufacture of the Wigand wire itself, which is quite complex. But if you have enough cards, you can just rejig the code. And the Wigand effect itself is actually quite cool. So you take your little bit of Wigand wire and you wave it past a magnet that's polarized in one direction, and it stores a little magnetic charge in the wire. And when you wave it past a magnet that's polarized in the opposite direction, it gives up that charge as a little pulse. And if you have a handy little coil of wire close to it, you get a little pulse of electricity, and that's what the sensor is. It's simply a little magnetic reed head next to the magnet, so that when that little wire goes beep, it picks it up. So we've got the Wigan technology itself, and from the back of a reader, you have what's called the Wigan electrical protocol. Now, pay attention, there will be a quiz on this later. There's two wires, and there's a ground wire, which isn't shown here. And the 1 wire carries 1 bits, and the 0 wire carries 0 bits. So basically, there's a small, they're normally held up at 5 volts, and there's a small dip to signify a bit. And if it's on this wire here, all the bits are 1s, and if it's on this wire here, all the bits are 0s. So 1, 0, 0, 1, 0, 1, 1. And it looks remarkably familiar to what you see here. Now, the trace on the top isn't actually of this card, but when you line them up, you see that this protocol basically stemmed out of the actual physical card reader itself. There were 2 sets of sensors, one reading the 1s, one reading the 0s, and as you swipe the card through the reader, that little 40 microsecond dip was the little pulse of energy given off by the wire. So we've got the actual card itself, we've got the electrical protocol, and this is what's actually sent down data-wise. There are many, many card formats, but kind of publicly to use, there's the universal format, which is 26 bits, and it's split up into a site code or facility code and an ID. And the leading and trailing bits are parity bits, so this performs even parity on the first 12 bits, and that performs odd parity in the last 12 bits. So not 24 bits is not a whole lot of security. And if you're a large company, the manufacturers will say, hey, we can make it more secure. We'll give you a 36-bit format, and we'll sell you your own site code or facility code, and we won't give it to anyone else, Mr. Large corporate. So, moving on to our friend, the proximity card. They're passive. I don't know if did anyone, hands up, see Adam Laurie's talk yesterday? Okay. He went through this a little bit. So they're passive. And when you hold your card up, the reader is emitting an RF field that powers up the card. And the card then starts chatting back with its ID. You can also have active cards, and they emit a field to the reader and have a very long read range. Vehicle tags are a good example of this. So this is what happens when you take a proximity card and you dip it in chloroform. I didn't do this, hasten to add, personally, but basically you can dissolve all the plastic off the card. And when you hold it up to the light, it looks very similar to those theft prevention tags. You think it's just a single foil antenna inside. What you actually have is about a bazillion turns of the finest wire you've ever seen in your life. It's nice to know that chloroform has a few more uses than killing puppies. So there's a difference. Now, generally, people talk about RFID, and they lump RFID and proximity tags together. They are different. Don't get confused. So proximity cards are magnetically coupled. It's a coil of wire, and inside the reader, there's another coil of wire. And they've got to be in close proximity for that magnetic coupling to work. It's like a transformer that you'd, standard wall wart. That's how that works. It's two coils of wire, close proximity. So it's got a short read range, and the card actually has a tiny little capacitor inside, and it stores up a little bit of power, and it signals back by shorting out its own coil. And that causes a very small volt drop in the coil, the energizing coil of the reader. And that's actually how it transmits the data back to the reader. Now, RFID cards, true RFID cards work with radio frequency. They have a long read range, and it really can be quite long. It can be, there was some guys at DEF CON a few years ago, and I think they were aiming for the world record. I think they got a read of about 70 feet from an RFID tag. The most I've ever seen one of these read is about 2 feet away. And generally, they have two antennas, one to receive power and energize the tag, and a second one to transmit the data back, which is normally done on a fraction of the frequency. For example, half the frequency is the frequency that it transmits on. And if you're an international traveler, HKIA is you'll see Hong Kong International Airport clear proximity tags on bags. They kind of pioneered it. And if you're waiting in kind of international baggage claim, have a look. And quite often people will peel them off and stick them on things. Very interesting. They tend to have, they tend to be clear labels with orange or yellow writing on them, and you can clearly see the two antenna and the little chip in the middle. Also, I came through Amsterdam a few months ago, and my bag tag had an odd red stripe across it. And when I took it off, I held it up to the light, and within the standard bag tag, there was a proximity tag as well. So again, if you're flying around, when you pop that tag off, hold it up to the light, and you might be surprised. So, in general, prox cards, they're energized, and they just start talking. Which is a bit of a problem, because as they may be energized by the reader in your office, they may be energized by the reader in my bag. Adam and I were at another conference in Norway a few weeks ago. We worked on a little demo, which we might set up later on today. But basically, we have a long-range reader. It's good for about 2 feet. And it's hooked up to a computer with a camera. And the trick is, if we'd actually got our act together this morning, it would have been set up at the coffee station out there, and everyone that walked up to the coffee station, if they had a prox card in their pocket, it would have read the ID off the card, and then it would have taken a photograph of them and tattooed the card number on the bottom of the photograph. A little bit worrying. So high security cards can be 36, 40 bits. Card readers will read, standard card readers like this will read up to 84 bits. I've never seen an 84-bit card. but they may well exist. And as I mentioned earlier, security is quite often by manufacturers restricting site codes, i.e., pay me a lot of money and I'll only sell you cards with site code X. I gave this talk at DEF CON, and there was a very good breakout session where there was quite a few people from the industry. It was a really good kind of group discussion, and someone pointed out that if you go to China or Taiwan and basically say, oh yeah, I want this site code and I want this range of IDs, they'll just knock them up for you. So that kind of level of security is diminishing rapidly. The world, party foul, the world generally uses 26 bits. So there's various proprietary formats. There's standards as well. This is a unique proximity tag. And those that went to Adam's presentation yesterday, he saw a little demo. The tag he had was slightly larger than this one. So it contains 8 bytes of unique ID, and it barfs the ID out when the tag's energized. Here's something slightly disturbing. If you're in the UK and you have a burglar alarm that has a police response to the alarm, so it's connected to a central station, and if the alarm goes off, the police will come out. Generally, a lot of them are unique tags, but basically the police now mandate that you can arm your alarm using a code, but if it has a police response, you must disarm it using a tag, which I thought immediately was a bit short-sighted, because I don't know where you're going to put your tag, but 99% of the people will put it on their house key ring. So it's nice and convenient. You just unlock the door, you use your tag to disarm the alarm. Of course, if you happen to drop your keys in front of your door as you're walking away after you've locked the house up, then you're totally screwed. So there's been various kind of people claiming to clone cards, and if you went to Adam's talk yesterday, he would have pointed out one of the comments that came back from the security industry, which is these cloners are not true clones because they don't have the same form factor as the original tag. So this is Chameleon. It's doesn't have the same form factor as the tag, so it's not a clone. It just happens to transmit exactly the same card ID as the real tag. So I'm going to give you a quick demo. Standard demo disclaimer applies. It's a demo, so it's just not going to work. However, if it does, totally going to take all the credit for it. So, hopefully, we have a little tag reader here. I'm going to clean this screen up. I'm actually going to just disconnect and reconnect it. So, here's my original tag. as you can see, this is the ID, C46. Well, it ends in C46 anyway. And here is my, it's not a clone. Looks remarkably clone-like to me. And if I just, let me just flip back to our slides here. So basically, we have a coil of wire and a capacitor, which forms a resonant circuit. This oscillates nicely at 125 kilohertz, which is the field put out by this reader. And here you have a transistor, which shorts across the capacitor and coil, and uses it to create that little dip in power at the reader. And this is a PIC chip. It's small, it's cheap, it costs $1.50, I think. And there's a few other components here, but basically, you pretty much need a PIC chip, a transistor, a capacitor, and a resistor, and a little resonator to make the PIC chip work. And that's it. That is the totality of the hardware that you actually require to emulate a unique tag. But of course, it's not a clone, and I didn't break into my house using the exact same ID as my alarm system, because that just doesn't happen. Okay. Then we have contactless smart cards, which, in my opinion, are the way to go. There's actual authentication between the card and the reader. There's strong crypto, which is quite cool. And there's a reasoned conversation. You can't just walk by, clone the card. You know, there's a bit of thought gone into it, which is nice. So I'm going to take a quick swing through biometrics. We've got the Retina Scan, my favorite. Iris scans, which are becoming very popular with governments these days. A new one, which is the Vino hand or finger map, and geometry scanners, and the good old fingerprint. So, and you'll see this as a recurring theme in the biometric section. We have an image capture and feature compare. With fingerprints, they tend to use two technologies. You have optical sensors and semiconductor sensitives, which tend to be capacitive. But they both take images, so even your semiconductor sensor is actually just an image device. Quite easily defeated. Gummy bears, sadly, licked photocopies of fingerprints. It's slightly disturbing. Also, depending on the reader, some readers have a little bar that you swipe your finger over, and some readers have platens that you place your finger on. Can anyone tell me what happens when you take your finger off that platen? You leave your fingerprint on the platen. So again, if you know, there's a little bit of training, you know, it's like smear your fingerprint off, because someone literally can come up, lift your fingerprint off the reader itself, duplicate it using one of these technologies, and you'll discover yourself owned. So the way the actual software analysis works is you've got your image, and the algorithm looks for standard fingerprint patterns. So here we have a ridge that ends, an enclosure as it loops around a little bit of skin, a bifurcation as the ridge splits, and a little spot, which is an island, or could just be a little bit of, could even simply be a little bit of dirt trapped in your fingerprint. And the software, depending on the algorithm, and this is kind of something you need to be aware of as well, is who is writing the algorithm to actually analyze the fingerprint. How good is that algorithm? Because it could be looking for relatively common features and doing a poor job at mapping them out. There might be a fraction as many of these, and your level of security goes down. So that's something that's not really talked about in detail in biometrics. Someone will sell you a fingerprint reader and you'll try it out and it works. And that's absolutely great. But the algorithm that's actually doing the detection work, generally you have no idea how well that's crafted. And that algorithm pretty much is your security. Hand geometry scanners. I have several of these, and they're quite nice because they're quite easy to use, and that's another issue with biometrics is ease of use. So they're reasonably easy to use. Yeah, my mother can use them. And here you have an image. Again, it's just another image. So here, you can actually see what the camera, which is mounted above here, actually sees. And this is actually quite a nice hack, because when they first came out, this was your image. And then some bright young thing thought, well, if I put a mirror at 45 degrees in the field of the camera, I can take a slice across, and I can see the profile of the hand as well. So then they came out with the hand key 3D, and you have your scan. I actually briefly owned, and I say briefly, I couldn't take it home for me because it was just basically, not to put a finer point on it, fucking huge. An original ex-military hand geometry scanner, which was close to being the top half of this podium, had a physical scanning element that moved up and down inside with an arm and a crank, and suspended over to the platen was a large infrared heating bar like you'd find in an electric fire to provide the infrared illumination. And it did work, but yeah, slightly ginormous. I ended up deciding that actually it probably wasn't worth the cost to actually FedEx it home. So this captures images again, just to recap. We can see the pegs here, and these are to align your fingers. And alignment is very important in biometrics because, as being humans and being basically big bags of kind of water, we're all a bit floppy and saggy, and we don't necessarily put things in the same place twice. So getting things to line up so you can actually take your measurements is a big deal. Slightly worrying is the template for your hand here is 8 bytes long. So it's not actually taking a lot of measurements. Even more disturbing for me, because I have several of them, I was at home, sadly enough, I was giving one of my neighbors access to a part of my house in case there's a fire when I'm away. So I enrolled him in the access control system and enrolled his hand in the hand geometry system and said, okay, so put your code in, you hit enter, and then you pop your hand on the platen, and this is how to do it. Being slightly brighter than me, he realized that when I entered the code, I actually didn't enter his code, I entered my code. And it let him in anyway, because apparently we have exactly the same hand geometry, which normally would be a cue for a movie and a life of crime together. But yeah, that was worrying. And as I said, the measurements here are only 8 bytes long, the template. So it just shows you that, holy crap, what's going on. The Vino hand scan is another image capture device. Similar to kind of fingerprints, I guess. This time it's actually using an infrared camera, take a picture of your hand, and then it subtracts it and actually works out where the veins are within your hand and uses that to create its code. Again, you've got to think, who is creating the algorithm? How much thought is going into it to actually make it secure? And there's little fingerprint kind of level ones as well. Iris scans. Now, I am enrolled with a program in the UK. So when I come back to the UK, I go into a lane that generally doesn't have many people in it. I walk into a booth. The doors close behind me, scarily enough. And a slightly crappy system asked me to put my eyes in the virtual spectacles. So you kind of jostle around a little bit. It takes a snap and touch wood up to now. It opens the doors on the other side. I don't have to present my passport, which was, if I was designing the system, you'd think, scan your passport with your little machine readable zone at the bottom of the page and compare who you're supposed to be with your iris scan. No, it apparently can identify me just from my iris scan alone. So again, it's just an image, which has a bit of a potential for walk-by captures. Again, if you've got a high-res camera, I can see this happening in the future. Now, the manufacturers did a test and they said, right, here, we'll prove that you can't do this. So they took they enrolled someone in the system, they took a picture of their iris and they printed it on a contact lens and proved that you couldn't do it. The only problem is the print on the contact lens, if you actually saw it, was so low resolution, it was a joke. It's like, you got to be kidding me. So I think you'll find that as high-res printing goes, this is going to be, you'll be able to pull this off in the future, if you can't already. And again, just another image capture device. Retina scanners, I have to say, my favorite. I own 3. They're more secure. It's a hard to steal credential because you've got to get up close and personal to the reader. The original readers, you actually had to rest your head on a little bar and look into the eyepiece. And now you can scan yourself from about an inch away. But unfortunately, they're a bit hard to use. And that kind of led to their downfall. So you need to kind of, a bit of practice, a bit of training. You can still screw it up. You can't use glasses. So, glasses have to come off every time you scan. And the manufacturer went bust, which is a real bummer. But it's a very good example how biometrics work. And I'm going to use this as a worked example as to how this thing actually works. So first of all, you walk up to the reader and you enter your code. Possibly, if you're me, take your glasses off. And you get a dot and a target displayed in the eyepiece. On the original devices, this was a little trail of dots that went off into infinity, and you'd scooch around so you could only see a single one. Put your finger on the scan button before you look in the eyepiece, because you're actually, when you get yourself aligned, you're actually going to have to hit the scan button yourself. So you look into the eyepiece, you shuggle your head around to line up the dots, and once they're on top of each other, you hit the scan button, and then you freeze for about a second. Now, I got my original Retina Scanner from a little place you may have heard of, which is called Hanford in Washington State. They manufacture quite a lot of weapons-grade plutonium and store it there. And they were having a bit of a garage sale, which they do every month. And someone bought a booth, and it had a scramble pad on the outside, a scramble pad and a Retina scanner on the inside, and a scramble pad on the other side to get in. On air conditioning unit, because it was parked in the middle of nowhere. So basically, you walked up to the unit, you entered your code on the scramble pad, walk in, enter your code for the Retina scanner on another scramble pad, take your scan, and when you step back, what the user's not aware of is the booth weighs you because plutonium, kind of heavy stuff. Still, if you knew what you were doing, you could still shed a couple of pounds and come out with your prize. So, not that easy to use. And also, all biometric devices have a variance factor, a bit of a fudge factor, because generally, you tend not to put your appendage in exactly the right place twice. You might be, retaining water and be a little bit bloated. So no two reads will ever be identical. So you need to have a bit of a fudge factor, a bit of leeway. So here's a Retina. It's not mine. And here is the target projected on the back of the Retina from the Retina scanner. So you hit the scan button, and the Retina scanners are actually electromechanical devices. So inside, you actually have spinning mirrors, and it scans a little circle on the back of your Retina. And it's reasonably simple. It's effectively almost a barcode. So there's the origin. And at 46 degrees, it got a little bit darker because we passed over a little vein. And the same at 88, and so on. The original IDs were 360 bits long. And it just shows you how these people think. They literally took a reading every degree and worked out whether it was dark or light. And then they add on the fudge factor, which is generally settable in these devices. You can make it quite tight, or you can loosen it off a bit. So my favorite, alignment is an issue. It's totally subjective. So when that target appeared in my dead center vision, it's not necessarily smack dab in the middle of my retina. It's where I perceive it to be in the middle of my retina. And that's almost like taking a brain print. So where I perceive that, as I grew up, as the nerves developed, I perceive this particular location to be smack dab in the middle. You've still got the fudge factor, which again is another way one of these systems can fail. If the administrator is getting a lot of users complaining they're getting bad reads, he can reduce the strictness of the alignment, and that can allow more false positives. You also have, in the case of the hand geometry scanner, if you have, if you're missing a hand, for example, you have the option to bypass that entirely and just rely on a code. So just because you see a hand geometry scanner, it doesn't necessarily mean that you need a hand to get in. The IDs also tend to end up as a hash, and that can have issues of its own. So we've got false acceptance rate, which is the rate at which the bad guys get in because they're thought to be a good guy. And then you've got the false rejection rate, which is how many good guys are actually bounced because the system doesn't recognize them. And this is a real balancing act, and it's a big issue with biometrics. Also, another issue is, like the UK passport system, just relying on the biometric itself to identify the user. You should always couple them with an ID. So you should say, I'm Fred, match me to my retina scan or my hand geometry scan, rather than saying, here's my scan, pick it out of the database yourself. I'm sure you'll find me. There's also issues of credential revocation. Big problem. Now, that's quite bad. Not nearly as bad as the... and unfortunately, I'm sure UK government, if I ever did have to revoke my credential, would provide me with a handy kit. But you probably wouldn't want to go through it a second time. So there's a bit of a problem with all these technologies. There's a bit of backwards compatibility in the security, and it's not always a good thing. Wigand, we talked about it before. Wigand cards were insanely popular because they didn't have the possibility of demagnetizing like Magstripe cards. They're, the readers, because you can encapsulate the magnets and the read heads behind epoxy, are pretty much bulletproof when it comes to the weather. So when Wigand cards came out, all the access control manufacturers ensured that their devices could interface with the Wigand readers. And they still do. It became a de facto standard. So all the readers, including the biometric ones we saw today, all use the Wigand electrical protocol and the data protocols to talk back to the access control systems. And that's a bit of a problem. It's plain text. It's easily intercepted. It's easily replayed. Includes the output from all those biometric readers. That's how the hand geometry scanner and the Retina Scanner and the fingerprint scanners are hooked back to an access control system. It includes the output from your strong crypto reader. So you just had a nice strong crypto conversation ensuring the data integrity of this card, and then it spits out its data over Wigand in plain text. So, Adam, can I grab you for a sec? Can you pass a few toys out? Okay, I hasten to add that when I now these are all dummies, and they're just to give you an idea of the form factor. I will say at DEF CON I got them all back, so it better happen with Black Hat. So the idea was to come up with a device that recorded Wigand IDs, that replayed them, was reasonably small, so check them out and pass them back. Were easily installable, so if you look at the device, one end is crimped shut and the other end is open. And so literally you just push the wires in and crimp them shut. Cheap, if possible. This proof of concept unit used PIC chips, which are quite cheap. So there are several challenges to overcome. How do I control the unit? I don't really want wires hanging out. How am I going to do it? Also, the drunk guy from the office next door just tried to enter your office. So people will use, in the regular day, bad cards against the reader. And if I actually want to get the data out of the device, how am I going to do it? So this is how a Wigand reader is connected to the access control system. You've got positive and negative, so power supplied to the reader itself. You've got the data 1 and data 0 Wigand lines coming from the reader back to the access control system. And generally, you've got a single LED drive line that goes back to the reader to turn the light on the reader green when you're allowed in. So what you've been looking at is a little device called Gecko. It uses command cards. It's got its own little set of cards to control its functions, like replaying. It uses the access allowed LED to validate the card. So when it sees a card ID go past, it looks at the access allowed LED and says, oh, did you just go high? If you did, I'll mark you as a valid card. And it also uses that access allowed LED to dump the data out. So with a PIC chip, you can say, line 5, you're currently driving that LED at the moment. Now I want you to be a serial port. 9600, 81, no parity. Here, take this lump of data and send it. So you can actually use the LED on the front of the reader with a small device to receive the data optically to read data back out. So now this device can be completely embedded behind the reader. No wires hanging out, no necessarily obviousness that it is there at all. So generally, readers have, certainly I've only seen one reader that it has tamper proofing. So there tends to be no tamper proofing on the readers. They are standard kind of devices generally. I mean, this is designed to fit on a standard J box, junction box on the wall. Same as your light switches. So literally, to prevent you getting at the actual wire transmitting the Wigand data, you have 2 screws and a plastic cover. I gave this talk to one of the DEF CON local groups in Minneapolis. And there was a couple of locksmiths there, and they said, ha, no problem at all. What you do is you just put in a couple of security screws to hold the reader on the wall. So that means if you try and get it off, you just total the reader. Okay, that's fine. Unfortunately, the readers cost $25 on eBay, and they don't transmit any unique data back to the reader. So, you know what? I'll bring a spare reader with me, and if I have to total the reader getting it off the wall, I'll just replace it with my own and pop the original cover back on. So this is what it looks like with Gecko in the system. It sits in line across all the wires, and you'll find out why in a minute. So it's monitoring and driving the LED, and it's monitoring and driving the data lines back to the access control system. So I'm going to give you another little demo. Again, standard demo disclaimer applies. Okay, so here I have a little access control system. It currently doesn't have a Gecko device inserted. Now, my 2 volunteers, I have Nicole, little round of applause for my helpers, and I have Adam, who is the bad user. Okay, Nicole, can you just swipe for me? Actually, can you just swipe again? That's what we like. So Nicole's in the building, bad user. No, not allowed. So what I'm going to do is I've got a little Gecko here in a harness, and I'm going to pop it in. So, Nicole, can you still get in? What about bad user? Okay, so basically, our bad user had the Gecko replay card. So he has just replayed Nicole's credentials into the access control system. So, I'm going to give bad user another quite handy card that controls Gecko. Here, have a go with that one. Try again. It's actually working fine. Nicole, pop into the office. You're not in yet, are you? No, Nicole's not getting in at all, but bad user, do you like to use your replay card? Bad user can get in. So the second card I gave him is a disable card, and it, as Gecko is inlined and is actually breaking the connection, I can control what data gets sent through to the access control system. So Gecko has been told with the disable card, don't allow any users in apart from our, yes, the new owner, our bad user. And actually here, use the enable card. And now Nicole should be able to get back in the building. So, thank you very much, guys. Yeah. So, it's amazing what you can do with a PIC chip and a little bit of plastic. So here we see a replay actually in progress. This is the card coming in. And as you can see, it's 01000. And this is the card data that's actually being transmitted out to the system, which is 00111. Yes, slightly worrying. So what you're seeing here demoed is the proof of concept version 1. It's got a very basic feature set. We can record, we can replay, we can disable, and we can enable. Version 2, slightly brighter. It can store multiple IDs in Flash. It checks, which this proof of concept doesn't, the validity of the card by monitoring the reader LED lines. It can download via the reader LED. And it can load data via command cards. So I've actually got a set of cards. I have a program card. I have a 0 card, I have a 1 card, and I have an end program card. So literally, you can go 0, 1, 1, 1, 0, 1, 1, and actually program an ID into the system. Version 3. This is a little Bluetooth device. So it's got all the functionality of V2, has a Bluetooth interface. You need it for biometric devices because obviously they don't have command cards to be able to inform the Gecko device what to do. And I'm beginning to get my act together. I've been playing with Chameleon devices for a little while, so I'm now kind of focused back on Gecko a little bit, and I'm starting to kind of integrate these features. There's a lot of nice things you can do with this. You can take your phone, and you can have the Bluetooth interface in Gecko just sit there querying for Bluetooth devices. And if your Bluetooth device happens to go by the name of Let Me In, it just does a replay and opens the door. And currently, when you talk to the Bluetooth version of Gecko, it gives you a handy little menu asking you what you'd like to do, because this is a tiny little Bluetooth serial port. Press 1 to open the door. Press 2 to download your data. Now, that's pretty small. And slightly larger, but still quite small, is this little guy here. This is a GSM modem. And actually, this guy, here are the 2 antenna ports. It's got 2 antennas because this is GSM and this is GPS. Form factor's a little bit larger than I would have liked, but you can monitor, you can really have remote access to the facility. And you could literally be on the other side of the world and open the door. This particular device, quite handily, is programmable in Python. And you can pick them up for about $100 odd from SparkFun Electronics. My fave. This guy here is about $40 and really is that small. So I'd like to say thanks to Video Man, who helped make my little demo unit. Major, Adam Laurie here, who kept me mostly sane during PCB design, which, if you haven't done it, is a bit of a head fuck from time to time. And he also donated the unique tag encoding method that we use in Chameleon. So thank you very much. And anyone have any questions? Everyone got everything. Excellent. In which case, I'll say thank you very much and bid you adieu.